Hello, I am Rohit, and today I would be talking about robotic telescopes. I have been using robotic telescopes for a while, and I would be sharing my experience on using them. And I would like to first thank Priya ma'am and Najam sir for giving me this opportunity. So I am an undergraduate student at Government College of Engineering, Nagpur, and I also work with a group called Global Supernova Search Team, which also happens to be a sky survey to search and study astronomical transients. And I will also be talking about that a bit later in my presentation. So, just to summarize few fundamentals about telescopes, as we know, based on refraction and reflection, we have two basic type of telescope, which is a refractor and a Newtonian reflector. And some modifications in the design of reflector gives us a CTK and a SCT reflector. And as you can see in the bottom right, there is an image which shows the working of this telescope. So once we have used either of these telescopes for visual observations, and if we want to take images of these objects, then we may have to use something called as CCDs, or the charge coupled devices, which will help you take the images of these objects. And as we have seen, that CCDs are sensitive to very faint signals that are coming from the celestial objects. Even our mobile phone cameras have CCDs, but they are not as sensitive to faint signals as what we are using in the astronomical imaging. So once after using this CCD and getting the images, and after we have processed the images we have got, we get an image of this sort that we can see over here is an image of Saturn. And one thing that one should remember is that in astronomy we are not dealing with formats like we are not dealing with formats like JPEG or PNG. We deal with something called as FITS, which is the flexible image transport system. And we have seen about FITS as well in the previous lecture, so I won't be diving into the details of those. So there are two ways that you can use a telescope. One is either manually or and other is automated. And if you want to use a telescope either ways, then you should be first familiar with the night sky. And if you are a beginner to if you are new to knowing the night sky, then you may want to use a software called Stellarium. And as we have seen, Stellarium is an excellent software. We have seen a demo on Stellarium as well. And if you are a beginner, then you may just want to go and go in the night sky and then use Stellarium to use Stellarium to locate stars and constellations and try to identify them. And if you want to get into the photography of the objects, if you want to take photographs of the object that you want to observe, then one thing that one should know is that it will depend upon the type of mount you're using. So you can use a telescope either manually or in an automated way. So if you're using a tracking mount, so what happens is if you observe an object through a telescope which has a manual mount, or you're using it manually, so you might have observed that the object that you're observing would move away from your field of view, and that happens because of the rotation of Earth. But if you want to take images of that object, then that is something that you don't want to happen. And uh, for that then you that for that to avoid that, you might want a mount which will track the motion of the object throughout the in the night sky, right? So you if you want to take the photographs of these objects, then you may want to use a tracking mount or an automated mount. And before you can go about using a tracking mount or take photographs of the objects, then you may want to perform some alignment processes. And depending upon the type of the mount, you will have to either perform a polar alignment or a two or a three-star alignment. So as I said, even if you want to get into visual observations or astrophotography, you will have to get familiar with the night sky and then perform the alignment processes to get good results. And if you are new to using a telescope, so there is a nice article that I am going to share with all of you. So it deals with what type of objects you can observe, what you can do with your new telescopes. So please do go through that. So, what exactly are robotic telescopes? So, robotic telescopes are the telescopes which can be used without human interference, and you don't need to be present at the site of observation. So, I can have my telescope up on my terrace, and I can use my telescope from my room, or I can even have my telescope at a much darker site and then control it from my room. So how exactly can I use a robotic telescope? So that actually would depend upon the type of mount you're using. So if you have a telescope which has a completely manual mount, then you might automate it with the help of motors and then run through codes which will help you to automate it. Or you can get a automator or tracking mount and then use something called as ASCOM, which will help you to communicate with your telescope. So ASCOM is a very good software which will help you to communicate with your telescopes, right from uh, telling your telescope to which object you want to observe to getting the images, all sorts of things. So why exactly uh, should we use robotic telescopes? So what are the advantages of using a robotic telescope? So one advantage is that, as I said, you don't need to be physically present at the site of observation, and you can schedule your observing run. So a robotic telescope has something called as a scheduler. So a scheduler will help you plan your observations, and if you plan to observe all throughout the night, then you can tell your telescope what sorts of objects you want to observe all throughout the night, and according to the scheduler, I mean what objects are uh, communicated to the scheduler, the telescope will observe those targets and get you the images. And if you're planning to build an observatory, say at on your terrace or a place far away from your home, a much darker site, or even in another country, then you can even automate your dome. And right from opening and closing the dome could be done with the help of few codes. So if you have a CCD, and if you are into doing some science with the fits, then you don't need to worry about getting into the site of going into the site of observations and then getting your fits. You can also automate that process, and if you can build a server, then it can help you get your fits right to your system, uh, and you can get your fits sitting in your home. You don't need to be physically present at the site of observation. And Stellarium, as I said, is an excellent software, and it can be also used to communicate with your telescope. So you can use Stellarium to tell your telescope what sort of objects I want to observe. So Stellarium will also do that, and it's very helpful. What after you get your fits images? So once you get your images, once the images are straight out of the CCDs, you might observe that the images are full of noise, and you might not want that thing to happen. So you may want images that are free of noise, which has less noise, right? And uh, no matter what you want to do with those images, so creating RGB images, if you want to create RGB images or do some science with the fits images, you might want to you might want images which have less noise. And if you look into the working of CCD, then you will understand what accounts for the noise in those images. And to reduce that noise, you will have to follow certain steps. And this is something called as image reduction techniques. And why do we need to do those things is something which I won't be diving into right now. So there are few certain steps that one needs to follow, and few reduction techniques called as, I mean, few reduction steps like bias frame reduction, dark frame reduction, and flat frame reduction. And if someone is into using CCD and working with fits, then they might be knowing what exactly is image reduction. And once you have successfully implemented those steps, once you have reduced your images, then you have an image which is uh, free of noise, and you can do great amount of science with those things. So can I use a robotic telescope without owning any type of telescope or even owning a robotic telescope? Yes, you can. Uh, there is a public robotic telescope service called SLU, and they have robotic telescopes in Spain and Chile, and they have a few telescopes coming up in Sharjah, and they have 5 robotic telescopes in Canary Islands, which is in Spain, and one of the telescopes is a solar telescope. And they have 3 telescopes in Chile. They have 3 telescopes in La Dehesa, which is near Santiago. So before I started working with the group, the reason why I started using robotic telescopes initially was to get familiar with the fits. So we are used to seeing these beautiful images of galaxies and nebulae, and we are awestruck by them. like it's really fascinating to see them. And even if we have a telescope and we want to, if we try to observe these galaxies or nebulae through the telescope, so sometimes their visibility might be hindered due to various factors, and it might not be even visible to you as bright as you might want. So what happens is, if you use a CCD to capture the images of the objects, the CCD, as it is sensitive to the very faint signals, it might bring out sharp details present in the galaxies and the nebulae, which you might not be able to see through your telescope. And if you see, if you look at those features, if you look at those images, then it's really fascinating. So the one thing that I wanted to do was to get familiar with FITs, to look at those sharp unseen details of those galaxies and nebulae, and just trying to get familiar with the fits and the softwares that are associated with analyzing the fits images. So fits has an interesting thing called as the fits header. So the header file will tell you the details of the images, right from the observation time, the time of the observation, the date of the observation, the type of filter that was used in observing this object, the name of the observer, the details of the telescope, the coordinates of the observatory, the filter in which the object was observed, all sorts of things. So uh, if you look at those things, then you will understand how a FITS works, right? And uh, after I was actually familiar with those things, after I was familiar with the FITS and the softwares, then I tried to get the WCS, and then I tried to get the array and deck of the objects in the images. And I then perform something called as astrometry, which is nothing but calculating the positions of the objects in the night sky, calculating the array and deck of the objects in the night sky. So uh, it is one of the most fundamental things. And once I could do the astrometry, once I could calculate the array and deck of the objects, then I could perform something called as photometry, which is nothing but calculating the magnitudes of the objects. And we have seen magnitude is nothing but the measure of its brightness, and magnitude will help me know the flux that is coming from the object. So it will help me know the brightness of the object. And to perform photometry, you should be perfect with astrometry. So these are very two basic things. And if you are familiar, I mean, if when I once after I was familiar with these two things, I tried to do astrophotography. I tried to combine images of galaxies in red, green, and blue filters to create something called as an RGB image, or the colorful images that we are seeing of galaxies and nebulae. And as you can see over here is an image of Andromeda galaxy, and uh, this slides primarily actually summarizes my aim of using robotic telescopes initially, and the result that I have got. And the reason why I've added the image of a cluster of galaxies is something I would be explaining in terms of the survey that I was talking about earlier, and which is the Global Supernova Search Team. So this survey was started as a collaboration between amateur astronomers in 2018 and amateur astronomers from India, from Canada, from France, from India, from US, and from Argentina. So it was initially started by it was started from the initial leads from Malhar and Cedric, and as you can see, Malhar is the principal investigator of this survey. And we are using an array of robotic telescopes which are in Canada, France, the SLUS robotic telescopes in Spain and Chile, and then in Argentina. And we are using this array of robotic telescopes to scan the sky and search astronomical transients. So transients are objects which have changing brightness. So we are looking for objects in the night sky which have changing brightness. And these are the photographs of some of the robotic telescopes that we are using. And uh, as we are using an array of robotic telescopes, so we are able to survey the sky up to declarations of up to minus 55 degrees in clear filter, and declarations greater than minus 55 degrees we are able to survey in sonar filters. So essentially we are an all sky survey. And As a result of using this robotic telescope, we were able to discover a supernova in the month of April. And as you can see on the left, we have an archival image from the digitized sky survey, and on the right, we have our own discovery image. And the supernova is here being marked by the green lines. And as you can see, it's nowhere to be seen in the image on the left. So I tried to do something called as image subtraction. So what we try to do is we try to survey the sky every possible clear night and then look for objects which have changing brightness. So over here, the subtracted image as I was saying is, so what I tried to do was I had an image of the same galaxy of the same part of the sky a few days back before discovering the supernova, and I subtracted it with the discovery image to clearly see the supernova. And the supernova's discovery magnitude was about 17.55 in clear filter. And if you type its name on Google, SN2020 EES, and look its detail on the transient name server's website, then you can also see which other large sky surveys have reported its discovery. And you can also look at its spectrum, because this supernova turned out to be a supernova type 1A. And as you can see, the host galaxy of this supernova is NGC 5157. And this supernova was about 24.4 arc seconds away from its host galaxy. So, just to summarize my presentation, if you're planning to um, use slew or get familiar with fits, then you may want to try to know how you can get the image. You can try to understand how image reduction works, how image calibration works, and then try to get the WCS, then did the RA index of the objects, and then try to do astrometry and then photometry. And then, then you can, if you're familiar with the basics, if you are strong with the basics, then you can go with you can do any amount of science, you can do any type of science you are interested in. And then uh, there are good image scaling softwares like SAODS9 and AstroImageJ. And if you want to get into photometry, then aperture photometry tool, Astrometrica, even AstroImageJ can be used to perform photometry. And if you are familiar with Python, then AstroPy, which is the workhouse for astronomy now. So AstroPy is of course excellent, and then of course you can use AstroPy to do all those things. And here are the links that are associated with few fundamentals and also with few data analysis stuffs. And now I would like to conclude with my presentation, and I would be giving a short demo of slew and the robotic telescopes. Thank you.